Hey everyone, welcome to this course on feature engineering. If you have ever wondered why two machine learning models using the same algorithm can produce very different results, the answer often comes down to one thing: the quality of features. Over the next 8 videos in this series, we will build a very solid understanding of feature engineering, starting with the fundamentals and gradually progressing to more advanced techniques. Along the way, we will learn not just how different techniques work, but also when and why to use them in real world machine learning projects. And this course is not just theory. By the end of the program, we'll apply everything you have learned in a comprehensive industry aligned capstone project. We will work on a real world dataset and we'll build an end-to-end feature engineering pipeline, and we'll also gain hands-on experience solving problems similar to those you will encounter in a professional data science role. Most importantly, we will finish this course with a portfolio ready projects that you can showcase to your recruiter and hiring manager as evidence of your practical skills. So let's get started. So this course is divided into total of 8 modules, with each module building on what's learned in the previous one. Here is what we will be covering throughout this course. We will start with overview of feature engineering, then we will understand various numerical data and how to handle them. Then we move on to general feature engineering techniques and dimensionality reduction techniques. After that, we will read and understand about techniques related to data, text data, image data, time series data, and finally, we will also understand what automated feature engineering is all about. So let's get started with module 1, that is overview of feature engineering. This module lays the foundation for everything we will learn in the rest of the course. Before we start transforming features or building sophisticated machine learning pipeline, it is important to understand why feature engineering matters in the first place, what problem it solves, and how it impacts model performance. We will learn these concepts through practical examples and real world case studies. So the ideas are not just theoretical, but they are easy to relate as well. So, in this module, we will start by understanding what features actually are, why they matter, where feature engineering fits into the overall machine learning lifecycle. From there, we will clarify the difference between data preprocessing and feature engineering through a practical case study. Next, we will explore various key goals of feature engineering and different ways features can be created, transformed, encoded, and selected. We will then discuss why feature selection is so important, especially when working with very large data set. Finally, we will look at the challenges of high dimensional data. We'll understand the curse of dimensionality and wrap up by learning how different machine learning models determine which features are most important. So, let's start with module 1, section 1 today, that is Introduction to Feature Engineering. Let's begin with a simple question. What exactly is a feature? When we work with dataset, not every column is automatically useful to a machine learning model, right? Some columns can be used directly, while others needs to be cleaned, transformed, combined with other information before they become meaningful inputs. So in machine learning, a feature is simply a measurable property or characteristic of an entity that helps a model make informed predictions or decisions. You can think of feature as a piece of information that model learns from. The better the quality and relevance of these features, the better the model's chances of making accurate prediction. The easiest way to understand feature is always through an example. Think of feature as a measurable characteristic of a thing we are trying to analyze, which is also known as entity. For example, if the entity is student, the useful features might include attendance, percentage, or quiz score, right? But if the entity is a customer, useful feature might be the age of customer or the monthly spending. Similarly, for a house, features could be its area or number of rooms. For a bank applicant in a loan approval problem, the features could be his or her income, credit history, etc. that will help model assess the applicant credit worthiness. Did you notice the pattern here? The entity changes depending on the problem, but features are always the measurable piece of information that describes that entity and helps the machine learning model make better decision. Let's understand this with a real world example. Imagine you are a bank manager reviewing a loan application. A customer has applied for a loan, and your job is to decide whether the loan should be approved or rejected. So, to make that decision, you will look at several pieces of information about that applicant, right? Such as income, credit history, age, existing debts, and perhaps even the employment status. But here is a key question: do all of these factors matter equally? Probably not. Some features have a much stronger influence on the final decision than others. Identifying these important features is exactly what feature engineering and feature selection helps us achieve, allowing machine learning models to make more accurate and reliable prediction. So now that we understand what features are, the next obvious question is, where does this feature engineering fit into the entire machine learning workflow? To answer that, let's look at the machine learning pipeline itself. Now, think of this pipeline as the journey that takes us from raw data to a machine learning model that can solve real world problems. While the steps happen in sequence, the process itself is continuous. As new data becomes available, we revisit and improve the model, making the pipeline a cycle rather than a one time process. It all starts with data collection, where we gather the raw data needed for our problem. The next obvious step is data pre-processing. Here we clean the data, we handle the missing values, we remove inconsistencies, and prepare it for further analysis. Once the data is clean, we move to next stage, that is feature engineering. This is where we transform the pre-processed data into meaningful features that captures useful patterns and information. You can think of feature engineering as a bridge between prepared data and a machine learning model. The quality of these features often has a great impact on the model performance than simply choosing a more advanced algorithm. After feature engineering, we move on to model training, where we select an appropriate machine learning algorithm and train it using the engineered features. Next comes testing and deployment. We evaluate how well the model performs on unseen data, and if it meets our expectation, we deploy it to our production. Finally, we enter the monitoring and maintenance phase. Over time, data patterns can change, causing models' performance to decline. So, we continuously monitor the model, collect new data, refine features, and retrain the model when necessary, and repeat this entire process. So, as you can see, feature engineering sits between data preprocessing and model training. It plays a crucial role by converting prepared data into informative features that enable machine learning models to learn effectively and make accurate predictions. In practice, well engineering features often contribute more to model performance than the choice of algorithm itself. Now that we have seen where feature engineering fits into the machine learning pipeline, let's understand what actually happens during this step. The process is quite straightforward. We start with cleaned and pre-processed data as the input. The goal is to transform the data into meaningful task-specific features that a machine learning model can learn from. So, in other words, the output of feature engineering is not more data, it's better data, quality data. The ultimate objective is twofold. First is to improve the model's predictive performance, and second, to make the model easier to understand and interpret by ensuring that the features captures the most relevant information out of that data. So formally, feature engineering is the process of using domain knowledge along with the mathematical and statistical techniques to transform raw data into meaningful features that can improve the performance of machine learning models. Notice one important phrase in this definition: domain knowledge. That's because feature engineering is not just about applying formulas or writing codes. It also requires understanding the problem you are trying to solve. The more you understand the business context and business domain and the data, the better the features you can create. This is why feature engineering is often called as the art of data science. While machine learning algorithms follow well defined mathematical rules, designing useful features requires creativity, intuition, and a deep understanding of both the data and the problem domain. It is this combination of science and human insights that makes feature engineering such a powerful skill. Now let's move on to the next concept, that is data pre-processing versus feature engineering. At this point, it is important to understand the difference between data preprocessing and feature engineering. These two terms are often used interchangeably, but they serve very different purpose. Both involve transforming data, but the intention behind that transformation is completely different. Think of it this way: data pre-processing prepares the data for machine learning, but feature engineering improves the data for machine learning. A simple rule of thumb is pre-processing fixes data problem, feature engineering adds business value. So during pre-processing, we are focused on making the data more clean and usable. This includes handling missing values, removing duplicates, correcting inconsistencies, or scaling numerical values so that algorithm can process the data correctly. Whereas feature engineering, on the other hand, goes a step ahead. Instead of just cleaning the data, it creates or transforms features in a way that helps the model better understand the underlying problem and make more accurate prediction. So here is an easy way to decide which category a transformation belongs to. If a transformation simply makes the data structurally usable by a machine learning algorithm, then it's a data preprocessing. But if that transformation introduces meaningful task specific information that improves the model's ability to learn, it's feature engineering. That distinction is important because pre-processing ensures the model can learn from the data, whereas feature engineering helps the model learn better from the data. Let's make this distinction more concrete with a simple example. Imagine you are building a machine learning model for a bank to predict whether a loan application should be approved or not. And one of the column in your dataset is obviously applicant's date of birth. Now you ask yourself, does the bank really care about the exact date someone was born? Not really, right? What the bank is actually interested is in the applicant's age, because age is much more relevant when accessing factors such as financial stability or credit risk. So instead of using date of birth directly, we can calculate the applicant's age using a simple transformation. So what we'll generally do is basically we'll extract the year from the date of birth, and from the current year we'll subtract that year, and we will arrive at the age of the applicant, right? So notice what's happening here. We are not fixing a data quality issue. The date of birth is already clean and perfectly valid. Instead, we are converting it into a new feature that carries more meaningful information for the prediction task, right? This transformation uses our understanding of banking domain to create a feature that is more useful for the machine learning model. That's exactly what feature engineering is all about. It's not just transforming data, it's transforming data in a way that makes it more relevant for the problems you are trying to solve. In this example, age becomes the feature the model learns from, while date of birth simply serves as the raw information which is used to create it. The interesting part is that the exact same transformation can be either pre-processing or feature engineering. The difference is not the code, it's the intention behind it. So let's take two cases here. We'll see when it is a data pre-processing and when it is a feature engineering. So let's start with case 1. Suppose your machine learning algorithm does not accept date values and only works with numeric inputs. In that case, you convert date of birth into age simply because the model needs a numerical value, right? You are not making any assumptions about whether age is important for the prediction or not. You are just making the data compatible with the algorithm. In this situation, the transformation is data pre-processing because its purpose is purely technical. Now moving on to case 2, when is it a feature engineering? Now consider a different scenario. You are building a loan approval model, and based on your understanding of banking, you know that age influences financial behavior and credit risk. Younger and older applicants often exhibit different borrowing and repayment patterns. So you deliberately create the age feature because you believe it will help the model to make better predictions. Here, the transformation is driven by domain knowledge, not the technical requirement. The goal is to provide the model with more meaningful signals. That makes it feature engineering. So remember the key idea. The code may be identical, but the purpose behind the transformation determines whether it is a pre-processing or whether it is a feature engineering. So that's one of the most important distinctions to understand before moving forward.